non-fancy definition of it is. A rational function. What is a rational function? Like, someone read the fancy definition.
Function that has a ratio of two polynomials.
Perfect. A ratio of two polynomials. What is a ratio? Starts with an F. Fraction. So these are fractions. And it said a polynomial, which means you have variables in both numerator and denominator. So it's a polynomial on top, polynomial on the bottom. So it's different than if you were to just have like x plus 7 over 3. The key part is you want to be able to have ratio or variables in both parts. So they're fractions. You're going to probably have variables in both parts. A vertical asymptote. What is a vertical asymptote? Which way is vertical? Up and down. And then the moniker of a vertical asymptote is, does the function equal it or get close to it? Gets close. So it's a vertical line. The function approaches. You cannot cross it. When you look at it graphically, a lot of times in a graph, and I'm just making this up, they get shown as dotted lines because as a person that is graphing, it is tough to be like, it gets really close to it, it gets really close to it. So a vertical line is a line that the function is going to approach, but it's never going to actually equal it. It just gets really, really close to it. A hole. What is a hole? What does it look like on the graph? Open circle. So a hole, it is called removable discontinuity. I'm just going to draw a little open circle right there, and it comes from reducing your fraction. So a hole is considered removable discontinuity because technically you remove it. Did anybody run across what a vertical asymptote is considered? These are considered non-removable discontinuity. So they're both discontinuous. The idea about a function being continuous is you should be able to draw the entire thing without lifting up your pencil. If you have a vertical asymptote, you're going to have to lift up your pencil to go to the other side of it. And then if you have a hole, what that ends up looking like is the function is going to be fine and normal until a certain part. And then you're going to have a hole, and it's going to go to the other side. So a hole just means something reduced out at that point in the equation, which means if we go to the original domain restrictions, it's not going to work. A horizontal asymptote. Which way does horizontal go? Left and right. So a horizontal asymptote. A vertical asymptote is what the graph approaches. What would a horizontal asymptote be? It ends up being the end behavior of what it's approaching. And then the thing about a horizontal asymptote, you actually can equal it. So a horizontal asymptote just means what are the tails of your graph doing as your graph goes out to infinity? What are they doing? What kind of number is it leveling off to? A lot of equations and a lot of functions don't have a horizontal asymptote. What is one from Algebra 2 and Pre-Calc that does have a horizontal asymptote? Exponentials do. What number for an exponential does it get really close to but it never equals? 0. So horizontal asymptotes, it's the same idea, except for technically you can cross a horizontal asymptote. Sometimes you'll have like pieces of a graph that they'll oscillate around the asymptote. but horizontal, you can technically equal them. Vertical, you cannot. A slant asymptote. If a horizontal asymptote was horizontal, what would a slant asymptote do? Diagonal. So this is just a diagonal asymptote. It's the same idea as all the other ones. If you have a slant asymptote, it just means the function is going to get close to that diagonal line. These all have different instances and like how you find them, but it all really depends on just like the setup of the fraction. Just so you guys know, like we're going to do as many notes as we can today, finish them on Wednesday, finish the lesson up on Thursday. So this is like a 3-day thing, because if you go through the rest of this packet, this is kind of the big thing of all of the what's left. I think we have 3 sections left technically. Okay, we are just going to jump into it, and we are going to find vertical asymptotes and holes. So vertical asymptotes are lines that they can't equal. If we're specifically talking about fractions, what is something a fraction cannot equal? Where can't we have a 0? Denominator. So a vertical asymptote is when the denominator equals 0. So if you look at the first example, x over x plus 1, to find a vertical asymptote, you take your denominator and you set it equal to 0. Vertical asymptotes are pretty much just domain restrictions. So you find your vertical asymptote by taking your denominator, set it equal to 0. Where would our vertical asymptote be? X equals -4. Holes come from factors that cancel. So if I look at that first equation, is it even able to factor? No. So this one should have no, not applicable, no holes. For day 1, the way you check it is you now jump over to Desmos and you type in that equation. If you want a fraction, just hit the fraction bar first, like hit the slash first, and then you can just do your x over x plus 4. And if you zoom out, do we see how when x equals -4, up and down the line does not cross it? And then if you pick a point on here, you can drag it and it'll give you any value you want. All right, vertical asymptote, that's what it looks like on a graph, because obviously it won't put in the dotted lines. Next one, if we want to find a vertical asymptote, step 1, what gets set equal to 0? The denominator. And then if you want to find any holes, what do you have to do to find the holes? Factor it. When you have an option for both, is this one going to be factorable? Do your factoring first. So when I do this factoring, how do I factor the denominator? X and x, and then what was it? -3 plus 1? So if I factor it first, do I have any factors that are going to cancel? X plus 1. So then what's left over? 1 over x minus 3. When you're looking for your vertical asymptotes, you want to use the final version of it. So looking at the final version of it, instead of having x squared minus 2x minus 3 in the denominator, now it's in the denominator. X minus 3. So then where would our vertical asymptote be at? 3. The holes. The holes come from the factors that reduce away. What factor reduced away? X plus 1. So you do the same thing. You would set it equal to 0. So what is the x value of our hole? -1. So our end goal is we are going to be graphing these. An asymptote is a single line, vertical, horizontal, slant. A hole, though, is a point. So depending on how it is phrased, if it just wants the x value of the hole, you're done right there. If you want to know the full point, which is what we're going to have to work to anyway, if I know the x value is a -1, how do I find the y value that goes with it? Plug it in. So go ahead, plug that -1 into that equation.
Do you plug it into that original equation?
Yes.
So not the new one?
+1. Oh, plug into the new one. Sorry, it won't exist on the first one. Good point. Yes, so plug into this guy right here. So if I plug in -1 into that, what fraction do I get? -1/4. So our whole is at x equals 1. The point of it would be -1, -1/4. When you look at this graph, graphically, again, do your slash. I'm going to graph the original one. So x plus 1. All right, so pretty easy to see. We have our vertical asymptote at x equals 3. Holes, though. Holes don't really show up on graphs. What we can do, though, what x value do we have our hole at? -1. So if I just take a random point, do you see how it'll like real time update it? As soon as I hit -1, it's going to say undefined. So that is how holes show up on Desmos, because they can't physically draw in a circle there, because like any little point next to -1 is going to be there, so it's going to get filled in. But if you drag to where the hole should be, it's undefined. The difference is, and this is kind of like a preview as to how we think about it in calc and why this works. If I were to graph the other function, like what we had when we were left over, do you see how they look to be the exact same? Like I can turn this off, it's blue, put it back on, it's green. If I take the new one now, do you see how that hole's been filled in? So algebraically, these two equations are the exact same, except for at the point of -1, because -1 should have a hole at it, because our starting equation, we were able to factor that away. But in reality, these two equations are the same except for at the one point, which is why when we plugged in to find the hole, you have to plug into the new one, because if you plug into the original one, you're going to get 0/0. Okay, next one. Step 1 on number 3. Can you factor? No. So you can't cancel out. So right away, if you can't factor it, look to see if anything cancels. Can you cancel an x with an x squared when it has that +4 with it? No. So we know there are no holes. Holes come from when you can reduce out, cancel your factors. Vertical asymptote. What part gets set equal to 0 to find your vertical asymptote? The denominator. When I set this denominator equal to 0, solving it wise, what would be the first thing you do? So what does x end up equaling? Plus or minus 2i. Do imaginary answers exist on our x-axis? No. So is this graph going to have any vertical asymptotes? No. Absolutely nothing wrong with hopping over to Desmos or your graphing calculator or anything like that, because if you can see it, it makes it a bit more believable. We can see it has no breaks in it up and down, no holes in it. So no breaks on this one. Okay, you guys try the last one. Find your vertical, horizontal, or vertical and hole. Find the holes first, aka do your factoring, and see if anything will cancel out. So vertical asymptotes are called non-removable discontinuities because you can't cancel them. It's what's left over after you've done your canceling. So vertical asymptotes, non-removable, no matter what, they're always going to be there. Where is this one's vertical asymptote at? 3. Poles are called removable discontinuity because they come when you remove or cancel those factors. What is the x value of our hole? -7. So whatever you cancel out, you said that one equal to 0. To find the whole point, you just take that -7 and plug it into your new equation because it does not exist on the original one. So as a fraction, what is 1 over -7 minus 3? So x value wise, it's just going to be that. If you ever want the whole point, which is what we'll have to do once we start graphing these, that's what it's going to look like. Poles and vertical asymptotes are just domain restrictions. In a fraction, big thing is you can't have 0 on the bottom, and then since that x plus 7 cancels away, it's going to leave a hole. Do you guys have any questions on those two? All right, now we're going to talk about horizontal asymptotes. Horizontal asymptotes are essentially just end behavior. So it's what the tails of the graph are doing as you approach infinity. Horizontal asymptotes, if I would assume probably like a third to half of you guys will take a calc class. This is kind of one of the first things you do. Because when we talk about a graph as it goes out to infinity, it just means what is the limit of that graph as you go to infinity. There's a shortcut. That shortcut is just based off of a rule from calc. I'm going to show you guys the way to do it. You don't need to write this down if you don't want to, and then we'll talk about the shortcut. So, horizontal asymptotes come from dividing by the highest power of x. So when I look at this first example, what is our highest exponent on x? X squared. So I'm going to take everything and divide it by x squared. Reducing wise, if you have an x on top and an x squared on the bottom, what's that going to reduce to? 1x on the bottom. And then same thing here, x squared on top and bottom. So you start by dividing everything by the highest power of x, as long as you have a regular rational, like no fractions, or sorry, no radicals or anything like that. And then we're going to do something called the limit. The limit just means we're going to think about x as it gets really, really, really big. So if my x is getting really, really, really big, what is 12 divided by something really, really, really big? As you divide by really, really big numbers, what is this whole thing going to end up equaling? 12 divided by 100, 12 divided by 1,000, 12 divided by 1,000,000, 12 divided by 10 million. As I divide by really big numbers, what's 12 divided by something really, really, really big? Really, really small. It's 0. So as I divide by something really, really, really big, this will just be 12. It'll be 0. 3, there's nothing to worry about there. It's just a 3. And then same thing here. X is going to get really, really, really big because we're talking about it going out to infinity. What is 1 divided by something really, really, really big? 0 again. What's 0 divided by 3? 0. So the horizontal asymptote on this one is 0. Horizontal lines, are those x equals or y equals? Y equals. So that is technically the way these should be done. It's getting at a limit. It just means if you think about really big x values, what's going to happen to these numbers? It all kind of gets shortened down into a little phrase, and you'll see a lot of these. When I look at this one, Babo, this means if you're bigger on the bottom, what was our answer when our exponent was bigger on the bottom? 0. So the first one, Babo, if your numerator, how do I write this? I'm just going to write it out. If you're big on bottom, your horizontal asymptote is just going to be at 0. Because if your denominator is getting bigger than your numerator because you have a higher exponent on the bottom, that just means it's going to equal 0. Because if you take anything divided by something huge, which is infinity, it'll just end up being 0. But if you're big on top, then you have no horizontal asymptote. You'll also sometimes see it just written as undefined, but there's no horizontal asymptote. And then the last one, if your exponents are the same, so each exponents are the same, you divide your coefficients. And it's the leading coefficients. So this is all coming from a limit. In calc, you really build this up, but for now, we just kind of get to use it to our advantage. Because again, the idea is, as you get x values that are huge, 1,000,000, 10,000,000, 1,000, or like 1,000,000,000,000, whatever, what's going to happen to these values? So when I look at the next one, what's our exponent on top? X squared. What's our exponent on the bottom? So our exponents are the same. So if our exponents are the same, to find your horizontal asymptote, divide your leading coefficients. So what is 12 divided by 3? Our horizontal asymptote should be at y equals 4. Is there a way to check to see if this is right? Sure, you go back to Desmos. Was it 3x squared plus 1? So if I zoom out, up at 4 here, that's what it's approaching. So it's based off of the exponents, your highest degree, nothing else matters. On this one here, 7, what's our exponent in the numerator? What's it on the bottom? So is it bigger on top or bigger on bottom? Bigger on top. So if it's bigger on top, where's our horizontal asymptote? We don't have one. There is no horizontal asymptote. If you were to graph this, so just by changing that to a 3 up there, we can see this is approaching nothing. It's just going to keep going up, keep going down. So it's no definite value it's going to touch. Last one. What is our exponent on top? 1. What's our exponent on the bottom? 1. So if your exponents are the same, how do you find your horizontal asymptote? Divide them. So what's our horizontal asymptote? Negative 2/3. We are going to do one more thing with these because our end goal is to be able to graph. And when you graph, you can touch a horizontal asymptote. So to prepare us for graphing, once you know what the horizontal asymptote is, you then want to see if it is ever going to equal it. So we're just going to do one of these for the sake of time. But if I want to know, does this function ever touch its horizontal asymptote? I'm just going to set it equal to that. If a fraction is going to equal 0, what part of the fraction equals 0, the top or the bottom? The top. So technically, I mean, you could think of this as cross multiplying, where 0 times that equals 0, 1 times 12x equals 12x. Either way you get there. So at what x value does this thing equal its horizontal asymptote? So it will touch its x asymptote, or its horizontal asymptote at x equals 0. So vertical asymptotes are where the denominator equals 0. Horizontal asymptotes are looking at how the exponents of the top and the bottom relate to each other. And then the last type of asymptote is an oblique or a slant asymptote. This is the most unique and the least likely one you're going to come up to. This only happens when the degree of the numerator is one more than the that's not how you spell it, than the degree of the denominator. So this is a special case where these aren't going to have a horizontal asymptote because the numerator, it's bigger on top than it is on the bottom. However, if that degree is only off by 1, so like on example 9, we have a 2 and a 1, so it's only off by 1. This one will have a slant asymptote. To find the slant asymptote, we get to long divide. The reason you want a long divide is like example 9 would work for synthetic because it's linear on the bottom. Most of the time they're not going to. Like this one you couldn't use synthetic division anyway, so just use long division. When you do it, you're just going to divide like normal. For long division, leading term to leading term, how do you make an x into an x squared? And then you multiply down, so we have x squared minus x. What do we do to our signs? Flip your signs. So those are gone. Those are gone. Only thing left to do is bring down the plus 1. Can you make an x into a 1? No, so what is that one considered? The remainder. So here's kind of the nice part. Like normally we would write plus 1 over x minus 1. The oblique or the slant asymptote is just your answer without the remainder. So without the remainder, we just got an x. So our slant or oblique asymptote is y equals x. Which means if you were to graph it, that diagonal line, it would approach that diagonal line as you get further and further out. Next to it, do you see how the numerator is 1 more than the denominator? So you're going to do long division. How do you make a 3x squared into a 12x to the third? 4x, so then we get our 12x to the third, and then we are going to get a plus 4x, which means technically how many x squared, or sorry, just x, how many x's are in 12x to the third?
2, 4.
How many are in this like original one? How many x's are there? 0. So if you're missing a spot, when you do your long division, just keep in mind, like, you have a negative 4x because technically it was a 0 minus 4x. Can we make a 3x squared plus 1 into a negative 4x? No, so this negative 4x would be the remainder. Normally we would write it as minus 4x over 3x squared plus 1. But if you're looking for the slant asymptote, your slant asymptote is just the part without the remainder. So what is our slant asymptote going to be? 4x. Slant asymptotes are goofy. It's a super special case. The numerator just needs to be 1 more than the denominator.